Here's a proof by induction example that goes with our video on the monotone convergence theorem. You don't need that video for this example, but it will give you more background on what we're trying to do. We also note the difficulty level here may be higher than pre-calculus, so maybe more appropriate for real analysis. Now, our problem, we're going to have a recursive sequence. We define the first term a sub 1 to be equal to 0. Then, for terms in the sequence with n greater than 1, a sub n is equal to 1 plus a sub n minus 1 over 2 plus a sub n minus 1. We want to show that our sequence is increasing. So a sub n minus 1 is less than a sub n for n greater than 1. So the idea is, as we let n get bigger, the terms in our sequence are also going to get bigger. Now, first, to orient ourselves, let's check out the first few terms of our sequence. So I start with 0. I put in 0 for each a sub n minus 1. I get a 1/2 or a 0.5. Now, as we go down, so a sub 3 is 0.6, a sub 4 is 0.61538, a sub 5 is 0.617647. So we're going to be increasing for these first 5 terms. Now, the punchline from the other video is that these numbers are going to increase, but they're not going to go off to infinity. So they're going to level off at the number, okay, approximated by 0.618033, or square root of 5 minus 1 over 2. Now, the key to seeing that is to take your a's, replace them with l's, and then solve for L. Before we get to the proof, let's first do the work for the induction step. So what makes this problem difficult is that there's a trick, which is either you see it or you don't. Now, for the induction step, we're going to assume the kth statement's true. A sub k minus 1 is less than a sub k. We want to show that the k plus first statement's true. A sub k is less than a sub k plus 1. Our key is going to be to rewrite our definition as follows. So in our denominator, I'm going to rewrite that as 1 plus a sub k minus 1. Then I'm going to divide numerator and denominator by 1 plus a sub k minus 1. So when I do that, we'll turn our definition into 1 over 1 plus 1 over 1 plus a sub k minus 1. The key here, we've isolated the a sub k minus 1 in the denominator. So it's going to make our bookkeeping much easier. Now, this is what I want to show. So let's just set this up and then work backwards to see that I can get to our induction hypothesis. So I write this out for a sub k plus 1. Now, all terms that we consider here are going to be positive. So when I multiply through an inequality, we're not going to change the direction of the sign. So if we clear denominators, okay, this term goes here, this one goes here. We can take off the 1s to get to here. Then we can multiply by denominators again to get to here, take off the 1s, and then we have our induction hypothesis. So that doesn't look so difficult, but it takes some work to come up with it on your own. Now let's go through our proof by induction step by step. So proof by induction, our statement, P of n, is given by a sub n minus 1 is less than a sub n for all n greater than or equal to 2. We start with our base case, n equal to 2. We want to show a sub 1 is less than a sub 2. We've already calculated those. So that was 0 less than a half, and that's true. So we have our base case. For the induction step, here we're going to assume that the kth statement's true and use that to show that the k plus first statement's true. Now, we're assuming that a sub k minus 1 is less than a sub k, so we're allowed to add 1 to each side of the inequality. Then, because both sides are positive numbers, we'll divide both sides by 1 plus a sub k minus 1, 1 plus a sub k. So it just moves each term underneath a 1 on opposite sides. Then, I'm going to add a 1 to each side. And again, we're going to divide both sides by each term on the left and right. So it just moves this one to this denominator, this one to this denominator. Now, to finish, we just unravel each of these terms. So here I'm going to multiply denominator and numerator by 1 plus a sub k minus 1. Okay, that's going to go through, give us 1 plus a sub k minus 1 over 2 plus a sub k minus 1, which is a sub k. A similar trick turns our right-hand side into a sub k plus 1. Now, that means a sub k is less than a sub k plus 1, and that's our induction step. Since the base case and the induction step are true, that means our statement, P sub n, is true for all n greater than or equal to 2.